Welcome to our series on essential concepts and terminology in transportation planning. In this lecture, we will explore the fundamental concept of the traffic assignment.
Traffic assignment is the final stage of the conventional four-step travel demand forecasting model. In this stage, the origin-destination travel demand for each transportation mode, determined in the mode choice step, is assigned to the coded highway network. The input OD matrices are derived from the production attraction matrices developed during the trip generation and trip distribution stages. The resulting travel demand is then expressed in passenger car units, the standard analytical unit for highway traffic assignment. In this lecture, we will focus on vehicle traffic assignment on highway networks. A traveler's route choice is influenced by a wide range of factors. In addition to travel distance and travel time, route choices are affected by monetary costs such as tolls, road signage and guidance information, individually perceived route information, recurrent congestion, intersection signal delay, and highway geometric characteristics that may influence driving risk. However, to improve analytical efficiency and reduce multicollinearity among explanatory variables, practical applications generally use travel time and travel cost as the primary explanatory variables. Because these variables are measured in different units, they are combined through the concept of generalized cost, which uses the value of time to express travel time and monetary cost in a common unit. The fundamental behavioral assumption of traffic assignment is that travelers choose the minimum generalized cost among all available alternatives. Based on this assumption, traffic assignment models are broadly classified into deterministic traffic assignment, which assumes travelers have perfect knowledge of network conditions and always choose the minimum cost route, and stochastic traffic assignment, which accounts for perception errors and random variations in travelers' perceived route costs. In this lecture, we will focus on deterministic traffic assignment as it remains the standard approach in most transportation planning and engineering applications.
The mathematical foundation of traffic assignment theory is based on the two principles proposed by Wardrop in 1952. Wardrop's first principle provides the theoretical foundation for user equilibrium, whereas his second principle forms the basis of system optimum. Wardrop's first principle states that at equilibrium, all routes actually used between the same origin and destination have equal travel costs. Any unused route must have an equal or higher travel cost than those in use. From a behavioral perspective, this equilibrium results from each traveler independently choosing the route that minimizes their own travel cost. Consequently, no traveler can unilaterally switch routes and further reduce their travel cost. From a computational perspective, traffic flows are repeatedly redistributed among competing routes until the travel costs of all used routes converge to the same value, thereby reaching equilibrium. This user equilibrium state is generally regarded as the representation of actual route choice behavior observed in real-world transportation networks. In contrast, Wardrop's second principle seeks to minimize the total travel cost of the entire network rather than the travel cost experienced by individual travelers. Instead of representing autonomous traveler behavior, it describes a hypothetical system-wide optimum from the perspective of a transportation system operator and serves as a benchmark for evaluating network efficiency. Under the system optimum condition, some travelers may be assigned to routes with higher individual travel costs if doing so improves the overall performance of the network. Mathematically, this equilibrium is achieved when the marginal social cost, the additional cost imposed on the entire network by one additional vehicle, is equal across all used routes. In practice, user equilibrium assignment is primarily used to predict and reproduce real-world traffic patterns, whereas system optimum assignment is mainly used to evaluate transportation policies and establish desirable operational targets, such as congestion pricing and optimal route guidance strategies.
A link performance function is one of the fundamental components of traffic assignment models because it describes how congestion affects travel time on individual highway links. Specifically, it represents the relationship between the traffic volume assigned to a link and the corresponding travel time experienced on that link. For the mathematical formulation of traffic assignment models to have a unique and stable solution, the link performance function must be continuous, strictly monotonically increasing and convex. In other words, even when traffic demand exceeds highway capacity, the function must continue to produce increasing travel times as traffic volume increases, rather than representing the backward-bending flow density relationship observed under severe congestion. As a consequence of these mathematical requirements, conventional static traffic assignment models cannot fully reproduce complex traffic flow phenomena such as physical queue formation, spillback, and other dynamic processes that occur under oversaturated conditions. The most widely used link performance function is the BPR function, originally developed by the U.S. Bureau of Public Roads. The BPR function satisfies the mathematical conditions required for a unique equilibrium solution and includes two key parameters, alpha and beta. The parameter alpha is a scaling parameter that adjusts the magnitude of congestion. For example, when traffic volume reaches the capacity level, that is, when the volume to capacity ratio equals 1.0, the travel time becomes 1 plus alpha times greater than free flow travel time. The parameter beta is an exponential parameter that determines the sensitivity of travel time to congestion. As the VC ratio increases, larger values of beta cause travel time to rise more rapidly, enabling the function to represent the sharp increase in delay as traffic demand approaches or exceeds highway capacity. The link performance function is a critical component that determines the predictive accuracy of the traffic assignment model's representation of reality. Therefore, during the network calibration process, it is essential to estimate appropriate values for free flow speed, highway capacity, and the alpha and beta parameters based on observed traffic volume and travel time data, accounting for highway functional classification and regional network characteristics. In addition to the BPR function, other link performance functions, such as the Davidson and conical functions, are also used in research and practice, depending on the characteristics of the network and the objectives of the analysis.
A fundamental computational component of traffic assignment models is the shortest path algorithm. This algorithm identifies the route between a given origin and destination that minimizes generalized cost, such as travel time, tolls, or other travel-related costs. These algorithms are based on the fundamental assumption of perfect information, meaning that travelers are assumed to have complete knowledge of the costs associated with every link in the network. The basic computational mechanism is based on node labeling. Starting from the origin node, the algorithm systematically explores adjacent nodes while continuously updating two pieces of information for each node: the minimum accumulated travel cost required to reach that node and the corresponding predecessor node along the current shortest path. As the search gradually propagates throughout the network, every reachable node is assigned its minimum travel cost and predecessor information. Once this process is complete, the shortest path is identified by backtracking from the destination node through the recorded predecessor nodes until the origin is reached. The most widely used shortest path algorithms are the Dijkstra algorithm and the Moore algorithm. Another widely adopted method is the A-star algorithm, which enhances Dijkstra's algorithm by incorporating a heuristic estimate of the remaining distance to the destination. By guiding the search toward more promising directions, A-star substantially improves computational efficiency for large-scale network applications.
Traffic assignment is not completed through a single shortest path search. Instead, achieving user equilibrium requires an iterative process in which link travel times are repeatedly updated as traffic flows change, and shortest paths are recalculated accordingly during each iteration. In fact, these calculations typically account for the majority of the total computational time required by traffic assignment models. Therefore, the efficiency of the shortest path algorithm plays a crucial role in determining both the computational performance and the practical applicability of the overall traffic assignment model.
While Wardrop established the conceptual principles of user equilibrium and system optimum, it was Beckman who formulated these concepts as nonlinear mathematical programming problems that could be solved computationally. Later, LeBlanc and colleagues applied the Frank-Wolfe algorithm to transportation networks, making it possible to compute user equilibrium efficiently for large-scale real-world highway networks. The equations shown on the screen are Beckman's mathematical formulations of user equilibrium and system optimum. Both models share the same set of constraints, differing only in their objective functions. The constraints consist of three fundamental conditions. First is the flow conservation constraint, which requires that the total travel demand for each origin-destination pair equals the sum of the flows assigned to all feasible paths connecting that OD pair. Second is the link path incidence relationship, in which the flow on each network link is obtained by summing the path flows multiplied by the corresponding incidence indicator, delta. Third is the non-negativity constraint, which requires all path flows to be non-negative. The objective function of the system optimum model is relatively intuitive because it directly minimizes the total travel time of the entire network. In contrast, the objective function of the user equilibrium model is expressed as the integral of the link travel time function. As a result, its physical interpretation is far less intuitive. However, Sheffey demonstrated mathematically that the first-order optimality conditions of this integral formulation are exactly equivalent to Wardrop's first principle. In other words, the integral objective function is not intended to represent traveler behavior directly. Rather, it is an elegant mathematical construct designed to generate the user equilibrium solution. Sheffey further proved that the user equilibrium objective function is strictly convex. Therefore, a unique equilibrium solution exists over the feasible region defined by the constraints. An important point is that this uniqueness applies to link flows, not necessarily to path flows. Although only one set of equilibrium link flows exists mathematically, multiple combinations of path flows may produce exactly the same link flow pattern. Thus, the equilibrium solution is unique at the link level but may not be unique at the path level. This uniqueness property is particularly important in practice because given the same network and input data, the model always converges to the same equilibrium link flow solution. This ensures that the analysis produces consistent and objective results regardless of who performs the analysis. Consequently, it provides a rigorous theoretical foundation for the objectivity, consistency, and reproducibility required in transportation planning and policy evaluation. Furthermore, Sheffey demonstrated that the system optimum formulation can be obtained directly from the user equilibrium formulation if the average travel time in the link performance function is replaced with the corresponding marginal travel time. Consequently, system optimum traffic assignment can be obtained by applying marginal travel costs within the conventional user equilibrium framework. This provides an efficient and practical framework for solving the system optimum problem. A fundamental method used in computing user equilibrium solution is the all-or-nothing assignment. In an all-or-nothing assignment, all trips between a given origin-destination pair are assigned entirely to the current shortest path. If highway capacity constraints did not exist, the resulting traffic pattern would itself satisfy the user equilibrium condition. However, in real transportation networks where capacity limitations exist, travel time changes as traffic volume increases. Consequently, a single all-or-nothing assignment cannot realistically represent network equilibrium. Nevertheless, this simple all-or-nothing assignment procedure serves as the fundamental computational module within the Frank-Wolfe algorithm used to find the user equilibrium state. The computational procedure of the Frank-Wolfe algorithm, originally proposed in 1956, can be explained in the following steps. The first step is initialization.
Link travel times are initialized using free-flow travel times, representing uncongested traffic conditions. Based on these initial travel times, an all-or-nothing assignment is performed to obtain the initial link flow vector x. The second stage is direction finding. The current link flows x are substituted into the link performance functions to update the travel times. Using these updated travel times, new shortest paths are identified and another all-or-nothing assignment is performed to generate an auxiliary link flow vector y. The third step is determining the descent direction and step size. The search direction, d, is defined as the difference between the auxiliary flow y and the current flow x. Then the optimal step size, lambda, determines how far the solution should move along this direction. Mathematically, this process involves linearizing the nonlinear objective function and performing a one-dimensional line search to identify the value of lambda that minimizes the objective function along that direction.
The fourth step is the update of link flows. A new link flow vector x is calculated by applying the determined direction d and step size lambda. The fifth step is the convergence test. The updated solution vector x is evaluated to determine whether it satisfies the convergence criterion for user equilibrium. If the convergence criterion is met, the iterative process terminates. Otherwise, the algorithm returns to the second step and continues the iterations until the convergence criterion is met. In summary, the Frank-Wolfe algorithm repeatedly updates the traffic flow solution by determining both an appropriate search direction and an optimal step size toward the user equilibrium solution. Its major strengths are its solid mathematical foundation, simple computational structure, and guaranteed convergence to the unique link flow solution. Since each iteration requires only a shortest path search and a one-dimensional line search, the algorithm is computationally efficient and relatively easy to implement. However, as the solution approaches equilibrium, the improvement per iteration becomes progressively smaller. The search trajectory often exhibits a characteristic zigzag pattern, causing the convergence rate to slow significantly near the optimum. To overcome this limitation, several enhanced algorithms, including the conjugate direction Frank-Wolfe method and gradient projection method, have been developed and are widely implemented in modern traffic assignment software. The final step of the Frank-Wolfe algorithm is the convergence test, which determines when the iterative computation should terminate. Because the algorithm approaches the optimal solution progressively through repeated iterations, the computation cannot continue indefinitely. Therefore, an objective convergence criterion is required to determine when the current solution is sufficiently close to the user equilibrium state. The most widely used convergence measure in practical traffic assignment is the relative gap. The relative gap quantifies how close the current traffic assignment solution is to the theoretical user equilibrium solution. As shown in the formula, the numerator represents the total excess travel time, the difference between the total travel time under the current traffic assignment and the total travel time that would result if every traveler were assigned to the current shortest path. The denominator is the total travel time obtained under the current shortest path assignment. Consequently, the relative gap represents the proportion of excess travel time relative to the total shortest path travel time. According to Wardrop's first principle, once user equilibrium is achieved, all utilized routes between an origin and destination have identical travel times. Consequently, every utilized route is also a shortest path, causing the relative gap to converge to zero. In practical applications, convergence tolerances are typically set to 10 to the negative 3 or 10 to the negative 4. These values indicate that the assignment solution differs from the theoretical user equilibrium state by no more than approximately 0.1% or 0.01%, respectively, and is therefore considered sufficiently accurate for practical analysis. Selecting an appropriate convergence tolerance requires careful judgment.
If the relative gap threshold is set too small, the number of iterations required near the optimum may substantially increase, resulting in convergence stagnation, where additional computation produces only marginal improvements. Conversely, if the threshold is too loose, the resulting traffic assignment may not achieve sufficient accuracy, reducing the reliability of transportation planning and project evaluation. For this reason, practical traffic assignment software typically specifies both a relative gap threshold and a maximum number of iterations, ensuring that the computation terminates safely even when convergence becomes slow. Recent advances in optimization algorithms, including the conjugate direction Frank-Wolfe algorithm and gradient projection method, have significantly improved convergence efficiency compared with the classical Frank-Wolfe algorithm. These methods enable more accurate and computationally efficient traffic assignment even for large-scale transportation networks. In 1968, the German mathematician Bress described a phenomenon that appears to contradict common intuition. He showed that adding a new road link to a transportation network or increasing roadway capacity can paradoxically increase not only the total travel time of the network, but also the travel time experienced by every individual traveler. This counterintuitive phenomenon is known as Bress's paradox. Looking at the network on the left side, we assume that the total travel demand from node 1 to node 4 is 6 trips. Before the new link is added, travelers are evenly distributed between two symmetric routes, path 124 and path 134, with 3 trips assigned to each route. When the link performance functions are evaluated, the travel cost on both routes is calculated to be 83. Since both routes have identical travel costs, no traveler can reduce their travel time by switching routes. Therefore, the network is in a stable user equilibrium state. Now consider the network on the right. A new road, link 5, connecting nodes 3 and 2 with a travel cost of 10 plus F5, is added to the network. This creates a new alternative route, path 1, 3, 2, 4. Because each traveler seeks to minimize their own travel time, individual travelers begin switching to this newly available route. Eventually, the traffic demand is redistributed evenly across the 3 available routes with 2 trips assigned to each. Recalculating the link flows shows that all 3 routes now have an identical travel cost of 92, resulting in a new user equilibrium. Surprisingly, although a new road has been added, every traveler experiences a longer travel time. The tables on the screen summarize the numerical results of the previous example. They clearly demonstrate that when every traveler follows the user equilibrium principle and chooses the route that minimizes their own travel cost, the addition of a new road can paradoxically increase the total travel time of the entire network. Comparing the route-level results on the left with the link-level results on the right, we can see that after the new road is added, the travel cost experienced by every traveler increases from 83 to 92. Consequently, the total travel time of the network also increases from 548 to 552. The fundamental reason for this paradox is that each traveler makes route choices solely to minimize their own travel time, whereas overall network performance is evaluated from the perspective of system optimum, which seeks to minimize the total travel cost of the entire system. Individual travelers do not consider the additional congestion they impose on others when entering the network. In economics, this is a classic example of a negative externality and a form of market failure. This example provides 2 important implications for transportation planners and engineers. First, when travelers behave non-cooperatively and pursue only their own benefit, constructing a new road does not always guarantee better traffic conditions and can, in even rarer cases, actually worsen traffic conditions across the entire network. In other words, individual optimization does not necessarily lead to social optimization. Second, expanding roadway capacity alone is not always the most effective solution to traffic congestion. Along with traditional supply-oriented measures such as road construction and lane expansion, attention should be given to traffic operations and demand management strategies that improve the efficiency of the entire network. Therefore, before implementing major transportation infrastructure projects, transportation planners should carefully evaluate how changes in network topology may influence travelers' route choice behavior through traffic assignment analysis. Even with a completed highway network, continuous operational strategies such as congestion pricing and advanced traveler information systems are essential to guide system performance toward a socially optimal state.
In professional transportation planning practice, traffic assignment analysis is typically performed using specialized transportation modeling software capable of handling large-scale computational problems. Widely used packages include Transcad, EMI, Visum, and Cube. In order to produce reliable analysis results using these programs, it is essential to build accurate input data and configure model options that are appropriate for the objectives of the analysis. The primary input consists of the transportation network, which is composed of nodes and links. Nodes contain geographic coordinate information, while links include detailed physical and operational attributes, such as free flow speed, the number of lanes, highway capacity, link length, turn restrictions and turn penalties, link performance function parameters by highway functional class, and observed traffic volumes used for network calibration. These network data are combined with origin-destination matrices, which represent travel demand by transportation mode. Together, they form the fundamental inputs required for traffic assignment analysis. Before running the assignment model, the analyst must specify several important model settings. The first is the traffic assignment method. In most practical applications, user equilibrium assignment is the standard choice. However, depending on the research objectives, computational constraints, and network characteristics, other methods, such as all-or-nothing assignment for uncongested networks, stochastic user equilibrium for scenarios with perception errors, or system optimum assignment for policy benchmarks, may also be employed. The second is the convergence criterion. The analyst must specify both the maximum number of iterations and the relative gap threshold. In practice, relative gap values of 10 to the minus 3 or 10 to the minus 4 are commonly adopted. For studies requiring greater precision, additional iterations together with a lower relative gap value can improve the accuracy and reliability of the final solution. Third is the selection of output options. After the computation is completed, the analyst selects the desired output measures according to the purpose of the analysis. Typical outputs include link traffic volumes, travel times, and volume-to-capacity ratios, as well as network-level performance measures, such as total system travel time and average travel speed. These outputs provide both detailed link-level information and overall network performance indicators for planning and policy evaluation. Although modern transportation software greatly improves computational efficiency, the quality of the final analysis ultimately depends on the analyst. The accuracy of the input data, the selection of an appropriate assignment model and convergence criterion, and the proper interpretation of the results all require sound engineering judgment, professional expertise, and practical experience.
Like all forecasting models, traffic assignment models must undergo a calibration process to ensure that they accurately represent real-world conditions. Unlike the earlier stages of the conventional four-step travel demand model, traffic assignment is unique because its outputs, link traffic volumes, can be directly compared with actual traffic counts observed on the highway network. This makes traffic assignment the only stage of the four-step model that can be validated directly against real-world observations. In the earlier stages, trip generation, trip distribution, and mode choice, it is difficult to verify the true values for the entire population. By contrast, the output of traffic assignment consists of link traffic volumes, which can be directly compared with observed traffic counts at specific locations. Consequently, traffic assignment is the only stage of the four-step model that can be validated directly against field observations. Of course, it is difficult to determine whether discrepancies in assigned traffic volumes originate from the assignment model itself or have accumulated from errors in the preceding stages. Nevertheless, because traffic assignment is the final stage where direct comparison with observed data is possible, network calibration plays a critical role in improving the reliability of the entire forecasting process by implicitly compensating for errors introduced earlier in the modeling sequence. In practice, calibration of traffic assignment models does not usually involve conventional statistical parameter estimation. Instead, analysts perform network calibration by refining network input data and adjusting link performance functions so that estimated traffic volumes better match observed conditions while remaining consistent with local highway characteristics. Overall, model performance is commonly evaluated using aggregate validation measures, such as the root mean square error, the GEH statistic, and scatterplot analysis. However, because these statistics summarize network-wide performance, they cannot fully identify localized sources of error. Therefore, calibration should not focus solely on achieving acceptable statistical indicators. It should also include systematic adjustments to individual network components. A practical three-step network calibration procedure is outlined as follows. The first step is review by highway hierarchy. When systematic overestimation or underestimation is consistently observed for a particular highway functional class, such as freeways, arterials, or collectors, the free flow speed and capacity values assigned to that highway class should be adjusted to better reflect actual operating conditions. However, the alpha and beta parameters of the BPR function should generally remain unchanged, since they are typically established through previous empirical studies and represent the inherent traffic flow characteristics of each highway class. The second step is review by major corridor. Traffic volumes should be examined across corridors that compete with or complement one another. If a particular corridor consistently attracts too much or too little traffic, its free flow speed and capacity values can be adjusted to better reflect field conditions and achieve a more realistic distribution of traffic among competing corridors. The third step is location-specific review. For locations where substantial discrepancies still remain, local highway characteristics such as longitudinal grade, horizontal curvature, on-street parking activity, and intersection density should be carefully considered when fine-tuning free flow speed or capacity values. The most important principle throughout the calibration process is that behavioral realism should take precedence over mere numerical agreement. If analysts force the model to match observed traffic counts through unrealistic adjustments that contradict actual highway conditions or traveler behavior, the model may become overfitted, resulting in unreliable forecasts when evaluating future transportation policies or infrastructure projects. Therefore, every adjustment made during network calibration should be supported by sound engineering judgment, logical reasoning, and observed field conditions.
The conventional four-step travel demand model was originally developed to analyze and plan transportation systems at a macro scale, such as urban or regional scale. Therefore, the results of the final stage, traffic assignment, should also be interpreted within this macroscopic and system-oriented context. In practice, traffic assignment analysis is commonly applied in three major areas. First, from a transportation supply policy perspective, it is used to evaluate the economic feasibility of new transportation infrastructure projects, such as highways and railways, and to determine their appropriate facility scale. Second, from an operations and management perspective, traffic assignment is used to assess the network-wide impacts of policies such as transportation demand management, or TDM, congestion pricing, intelligent transportation systems, or ITS, and traffic signal optimization. Third, from an environmental and social perspective, assigned traffic volumes by vehicle type and roadway segment provide essential inputs for estimating greenhouse gas emissions and traffic noise impacts.
When using traffic assignment results for transportation policy analysis, analysts must recognize an important characteristic of macroscopic assignment models. Their primary purpose is not to reproduce accurate values at every individual location, but rather to diagnose the spatial and behavioral system-wide effects of transportation policies across the entire network. Accordingly, policy evaluation should not place excessive emphasis on the absolute magnitude of individual numerical outputs. Instead, the results should be interpreted as a consistent and objective basis for comparing the relative performance of alternative policies. Particular caution is required when estimating travel time savings, which often constitute the largest component of economic feasibility analysis. Link performance functions, such as the BPR function, are aggregate representations that simplify complex real-world phenomena, including oversaturated delay and dynamic traffic flow behavior. Consequently, the monetary benefits derived from traffic assignment should not be interpreted as exact economic values. Rather, they should be understood as a consistent evaluation framework for comparing the relative priorities of policy alternatives, thereby reducing the risk of distortion and misinterpretation in the decision-making process. In conclusion, traffic assignment is a powerful analytical tool for diagnosing and forecasting the overall flow patterns of a macroscopic transportation system. When analysts clearly understand both the model's inherent limitations and its appropriate policy applications, traffic assignment can provide a robust scientific foundation for objective, data-driven transportation planning and policy decisions.
The deterministic traffic assignment methods introduced earlier, including Wardrop's first principle and the Frank-Wolfe algorithm, assume that every traveler has perfect information about network conditions. Under this assumption, if one route is even 0.1 second faster than another, every traveler is assumed to choose that route. In reality, however, travelers differ in how they perceive traffic conditions. They cannot perfectly anticipate congestion or unexpected incidents, and their route choices are influenced by individual experience, familiarity, and personal preferences. Stochastic traffic assignment was developed to explicitly represent these perception errors and behavioral uncertainties. In practice, logit-based route choice models are the most widely used framework for modeling such probabilistic route choice behavior. An important prerequisite for logit-based stochastic assignment is the definition of a reasonable route choice set, consisting of routes that travelers are realistically likely to consider. Consider the simple 3x3 grid network shown on the screen. Between origin node 1 and destination node 9, 6 physically feasible routes exist. However, real travelers generally prefer routes that are simpler and follow higher-class roadways. Therefore, in this example, only Path 1, using the upper corridor, and Path 2, using the lower corridor, are assumed to constitute the reasonable choice set. The remaining zigzag routes are physically feasible, but are excluded because they are highly unlikely to be chosen in practice. To construct such realistic choice sets efficiently, both practical applications and academic research commonly employ route generation techniques such as the k-shortest path algorithm, link elimination methods, or constrained path enumeration during the pre-processing stage. Another important structural limitation of logit-based stochastic traffic assignment is the overlapping path problem. Its fundamental cause lies in the independence of irrelevant alternatives, IIA assumption. The standard multinomial logit model assumes that the random error terms associated with all alternatives are statistically independent. Consequently, it cannot represent the correlation between routes that share common links, resulting in biased route choice probabilities. Consider the example network shown on the screen. 3 alternative routes connect node 1 to node 6, and all 3 have the same total travel time of 4 units. However, paths 2 and 3 share link 5-6, whereas path 1 is completely independent. From a behavioral perspective, travelers are unlikely to perceive paths 2 and 3 as completely separate alternatives because they share a substantial downstream segment. Instead, they are more likely to compare the independent path 1 with the group consisting of the overlapping paths 2 and 3.
The standard logit model, however, treats all three routes as independent alternatives. Since they have identical utilities, it assigns each route an equal choice probability of 1/3. As a result, the probability of choosing the independent path 1 is underestimated, whereas the combined probability assigned to the overlapping paths 2 and 3 is overestimated. This is the well-known overlapping path problem. To address this limitation, several extended models have been developed, including the C-logit model and the path size logit model, both of which incorporate penalties for route overlap into the utility function. Alternatively, the probit model, although computationally much more demanding, is explicitly accounted for the covariance structure of the random error terms and is often implemented using Monte Carlo simulation. These stochastic assignment models are particularly important in mesoscopic and microscopic dynamic traffic assignment models, where realistically representing perception errors and en-route route switching behavior is essential. The user equilibrium model, based on the Beckman formulation introduced earlier, is a representative static traffic assignment method. Static assignment assumes that network conditions remain unchanged throughout the analysis period and therefore represents traffic as an average flow over that period. In reality, however, traffic conditions change continuously. Travel demand varies over time, traffic signals operate dynamically, incidents occur unexpectedly, and travelers modify their routes in response to real-time traffic information. Dynamic traffic assignment was developed to represent these temporal variations and the actual movements of vehicles through the network. Because time is aggregated in static assignment, unrealistic situations may arise in which traffic volumes exceeding a link's physical capacity are assigned to that link during the analysis period. In contrast, dynamic assignment explicitly tracks vehicle movements over time while respecting link capacity constraints. As a result, it realistically represents queues, delays, and spillback where congestion propagates upstream through the network based on traffic flow theory. Dynamic traffic assignment gains significant attention with the rapid development of intelligent transportation systems, ITS. As travelers increasingly receive real-time traffic information, they may adjust both their departure times and route choices, making time-dependent behavioral modeling increasingly important. However, simulating the movements of individual vehicles or vehicle groups over large urban networks requires substantial computational resources. Furthermore, reliable time-dependent origin-destination data, or dynamic OD, are required, and accurately estimating these data remains one of the major technical challenges. Moreover, dynamic traffic assignment integrates both travel behavior models, which determine trip frequency, destination, travel mode, route choice, and departure time, and driving behavior models, which represent vehicle acceleration, deceleration, car following, and lane-changing behavior. Consequently, both model development and calibration become considerably more complex. Therefore, static traffic assignment and dynamic traffic assignment should not be viewed as competing approaches, but rather as complementary analytical tools designed for different planning and policy objectives. Static assignment is generally better suited for long-term transportation planning and large-scale infrastructure evaluation because it is computationally efficient and provides a macroscopic assessment of network-wide traffic conditions and policy impacts. Dynamic assignment, on the other hand, is more appropriate for operational analyses such as signal control, congestion management, and real-time traveler information systems, where the temporal evolution of traffic conditions plays a critical role. Ultimately, every model is simply a decision support tool. Transportation analysts must understand the underlying assumptions, strengths, and limitations of each modeling approach, select the model that best matches the purpose of the analysis, and interpret the results within the scope of the model's assumptions. Recent advances in high-performance computing and the widespread availability of GPS-based mobility big data have accelerated the development of hybrid and multi-resolution traffic assignment models that integrate macroscopic, mesoscopic, and microscopic simulation approaches. Looking ahead, continued advances in AI-driven analytical methods and high-resolution real-time mobility data are expected to substantially improve the predictive accuracy of traffic assignment models, enabling more reliable transportation forecasting and supporting more effective, evidence-based transportation planning and policymaking. In the next lecture of our series on essential concepts and terminology in transportation planning, we will focus on the topic of the transit assignment. Thank you for watching. I would love to hear your thoughts or comments on today's lecture. If this explanation was helpful, please like and subscribe to support this series.